In the last video, we looked at the general mechanism for acid-catalyzed nucleophilic acyl substitution reactions. In the next couple of videos, we're going to apply that general mechanism towards some specific problems that we might face. So this acid-catalyzed hydrolysis of amides that we'll be looking at here is an example of a nucleophilic acyl substitution reaction. And as I mentioned in the last video with these nucleophilic acyl substitution reactions, they come in really two flavors, one being the acid-catalyzed scenario, which we'll be looking at an example of here, and the other a base-catalyzed scenario. So what we'll be looking for in these reactions in general is if we start with a carboxylic acid derivative, such as an amide, an imide, an ester, or an acid anhydride, for example, and we react with a nucleophile, what's going to happen is the heteroatom leaving group leaves and is replaced with the nucleophile during the course of the mechanism. So we'll follow the general mechanism we learned in the last video to apply toward this hydrolysis of amides reaction. And this reaction is very important biologically because amide groups are present within proteins. In fact, each of the individual amino acid building blocks that make up a protein are linked via amide linkages. And so a typical protein will have between about 100 and over 1,000 of these amide groups present within the protein molecule. And as the body metabolizes the protein, breaking it down into the individual amino acid building blocks as you digest your food, what's going to happen is that those amide bonds are broken through enzyme-catalyzed reactions that will go very much like the reaction that we are going to be talking about here. So let's take a look at this example reaction and write out a mechanism for this. In our reaction, we're looking at a molecule that has one amide bond. We are going to start here with this particular molecule. So this is going to be a secondary amide because our nitrogen has two direct bonds to carbon. And if we were naming this molecule, just to get started here, because I might give you the structure, I might give you the name if I were asking you a question about this, it would be referred to as N-methyl because the nitrogen atom has that methyl group directly attached to it. So N-methyl, and then our carbon chain here with the amide group at the end has a total of 5 carbons, 1, 2, 3, 4, 5. So it would be N-methyl pentanamide as the IUPAC name for this molecule. So we're going to take N-methyl pentanamide. We will react it with acid as our catalyst. And since we call this a hydrolysis reaction, hydrolysis means breaking with water. So we're reacting with water. By definition, when we say that something's a hydrolysis reaction, what that means is that water is being used as the nucleophile to break some other bond in the molecule. And the bond that we're going to break here is this weak bond between the carbon and the nitrogen leaving group during this acid-catalyzed mechanism. So going back to that topic of protein metabolism, when proteins are being degraded, the proteins have hundreds or thousands of these amide linkages present connecting the individual amino acid units. And what's going to happen is that water will come in that reaction in an acid-catalyzed fashion and be used to break this carbon-nitrogen bond and replace with a water group, a hydroxy group from water to be specific in the final product. And therefore, that would result in the breakage of the protein into its individual amino acid units. So we're doing kind of a simplified example of that here because we have just one amide linkage, but the principle is the same. So in this reaction mechanism, much like what you saw in the earlier video on the general mechanism, we're going to go through those same exact series of steps, starting with protonation because we have that acid catalyst present. The protonation step is going to result in protonating the carbonyl. So we can go ahead and show that by taking our carbonyl lone pair electrons, bringing those over to grab a proton from our acid. So oxygen, lone pair electrons come over, grab proton from the acid, resulting in our protonated product of this step. So we'll go ahead and draw out that protonated product of this step with that new oxygen-proton bond there. Positive formal charge now on the oxygen. Then we have our NHCH3 as well. And I'm just going to label this step as step 1 was protonation. This is exactly following the template that we saw in our general mechanism for this acid-catalyzed nucleophilic acyl substitution reaction. So we've protonated. Now next step in the lineup is that after protonation, we now have a very electrophilic carbonyl carbon. And so that electrophilic carbonyl carbon is going to be prone to being attacked by a nucleophile. And the nucleophile we have available with its lone pair of electrons here is our water. And so step 2 in our lineup here is the nucleophile attacks that electrophilic carbonyl. So let's bring in our nucleophile. That was our water, H2O, brings one of its lone pair electrons over. It's going to come in, attack the trigonal planar carbonyl carbon. The pi bond goes up onto the oxygen, like I'm showing. And this will give us a tetrahedral intermediate. So our NHCH3 still here. And now we have our bond to our OH group. That bond to the hydroxy group was from this carbonyl pair of electrons going up onto the oxygen. Now we have 2 sets of lone pair electrons on our oxygen. And we also have this new bond, which I'll show in blue, coming over to water, which was our nucleophile. So a new bond here to OH2, like so, positive formal charge on the oxygen atom now. Now onward to step 3. And step 3, in order to stabilize that oxygen, which has a positive formal charge at the moment, we're going to do a deprotonation step. And to deprotonate, we have a couple of options. One is that to deprotonate, we could use the lone pair electrons from this nitrogen atom here, because nitrogen is basic, and that nitrogen could come in and do an intramolecular attack to grab this proton right here, transferring the proton therefore onto the nitrogen. That would be an okay way to go. The other way to go about this is to bring in a second unit of water and use that water as the base to grab that proton from our organic acid. That's going to force the breakage of this oxygen-hydrogen bond, as I'm showing, and the electrons from that are going to land on the oxygen. So let's go ahead and draw out the product of that step. So we have NHCH3, lone pair electrons in the nitrogen. We have our hydroxy group. And we also have a second hydroxy group because our H2O lost a proton. So it's now going to be just OH, like this. As well, we would have created H3O plus. So we've regenerated acid catalyst at that step of the reaction. Now, in this next step, what we are going to do is protonate the nitrogen atom. So we are going to take acid, react it with this nitrogen base to bring a proton onto that nitrogen. And in the previous step here, if you had already taken this nitrogen and done an intramolecular attack to grab the proton from right here, then you would already have the proton on this nitrogen. You wouldn't need to do this next step. But if we're doing this intermolecularly, which is how I'm doing it in this example, we would need to do now a protonation. So we're going to protonate the nitrogen. So we'll go ahead and show that nitrogen protonation happening by bringing in our acid. So I'm just going to use H plus as my acid here. Nitrogen acts as the base, grabs a proton from whatever acid you're using, and that's going to lead us to our next intermediate here. We'll have NH2CH3 and a positive formal charge now on the nitrogen, because nitrogen now has 4 covalent bonds to it because it has 2 bonds to carbon, 1 to the carbon chain, 1 to the methyl group, and 2 to the hydrogens. We also have still our 2 hydroxy groups. We haven't done anything to those, so I'll plug those in. Hydroxy group, hydroxy group. And now onward to our next step. After we have protonated that nitrogen atom, now our nitrogen atom and the R group that's associated with it is going to be a very good leaving group because it will leave as a neutral molecule, something that has no formal charge once it breaks away. So when we break then this leaving group away like I'm showing here, that's favorable because the nitrogen then will have no formal charge on it. In order to stabilize the structure, the organic molecule further, what will happen simultaneous to that is that one of the 2 hydroxy groups will have a lone pair of electrons come down to make a pi bond. So we'll go ahead and show the outcome of that. So the outcome of that, drawing this all in here, is that we will have a carbon-oxygen double bond here. Oxygen going to have that extra proton on it because our OH group here, we took the lone pair electrons down and made them into a pi bond. That pi bond I am sketching out in blue here in our product of that. So we're going to then have a positive charge on the oxygen there. The other group that's directly bonded to that same carbon is the OH group right here. And so I'm going to go ahead and plug in that OH group. OH like so. And then our leaving group, nitrogen, has left. And so I need to draw that out as its own entity. So it's going to be NH2, CH3, one set of lone pair electrons on the nitrogen. That set of lone pair electrons from the nitrogen came from the breakage of the covalent bond. The bond I'm highlighting right here on our reactant side is what's breaking to give that lone pair electron set to the NH2. And so now we are almost down to the final step here. We are at the final step here. After this step 5, which I'll go ahead and write out in words, is that the leaving group leaves. And at that time, also the carbonyl reforms. And now, to get to the final product, all we need to do is remove 1 proton from this structure. And so I'm going to go ahead and try to zoom out on some of this so that we can see what we're doing here in this last step rather than trying to crowd it in. And in this last step, what we're going to do is step 6 is deprotonation. And in this deprotonation step, we bring in a base. That could be either the amine that we've just created right here, or additionally, there's lots of water floating around in the reaction mixture since it's a hydrolysis reaction. So we could bring in water because we have that available in the reaction mixture. Water acting as the base. Boom, grabbing a proton from the acid to create that final non-protonated carbonyl group. So I'll go ahead and write out my carbonyl group with its 2 sets of lone pair electrons now. Hydroxy group there. So the product of this reaction is a carboxylic acid. So what I'm circling here in yellow at the bottom would be the final product of this reaction. And so if you were in a scenario where you were given an amide starting material, you subjected it to a hydrolysis reaction, what you would need to do is keep in mind that in these nucleophilic acyl substitution reactions, you are always replacing the leaving group, which is the heteroatom, the nitrogen here in this case, that's bonded to the carbonyl. You're replacing that always with the nucleophile. The nucleophile here would be the water, and the water loses a proton along the way, so it becomes OH to give us our final product that has no formal charges in it. So the trick to this, other than just doing the mechanism, is predicting what the product of these reactions would be, even if you don't necessarily want to write out the mechanism. And in order to do that, you keep in mind that the leaving group is the heteroatom and whatever R group it's going to be bonded to. That leaves and is replaced with whatever is over here as your nucleophile reactant, removing a proton as necessary in order to result in a product that has no formal charge. So in this case, the amide group becomes a carboxylic acid group. So based on this is one example of a specific scenario where you may run into a nucleophilic acyl substitution reaction that is acid-catalyzed. keep in mind this is not the only possible acid-catalyzed nucleophilic acyl substitution reaction, and based on the general mechanisms that we learned, you should be able to be given any combination of a carboxylic acid derivative, an acid catalyst, and a nucleophile, and predict what the product would be and the mechanism for how to get there.